reminders, announcements before we start. The textbook is now officially in the Math Studio and on reserve in the library, so you can get it in both places. Still working on getting the solutions manual reprinted. The falling apart one is in the Math Studio, but sometime this week probably we'll have a nice clean copy in the Math Studio and in the library. And I will post the PDFs on Moodle of the solutions manual, which is not just the answers, but the whole solution. So if you get stuck, you can kind of really see what to do. Yes?
In this pack of notes, wherever it references the pretest.
Yeah, just ignore it. Yeah. Yeah, don't worry about the pretest. Let's see, what else? Oh, we have a quiz. Our first quiz is coming up this Friday. It is covering, I can't remember. Classes. You can bring a note card, yeah. Classes 1, 2, 3, and 4. So it's on the first 4 classes. Yes. Next Wednesday. Yeah. So each week's homework is always due Wednesday of the following week. So this Wednesday, the homework that's due is just classes 1 and 2. Yeah. And then next week, the homework that's due is classes 3, 4, and 5. Any other questions? So you might notice, so homework is due weekly. That is to sort of allow you to determine, what schedule works for you and when you can get your homework done. But our quiz Friday is on classes 1, 2, 3, and 4. The class 3 and 4 homework isn't due until the next week, but you should probably do it before the quiz. Anything else? Just ignore the pretest. Okay, so we started talking last class very informally about limits. We were talking about instantaneous velocity and how it was a limit of average velocity over tinier and tinier time intervals. So today we're going to be just a little bit more formal about what a limit is. Okay, so we discovered that the height of this ball that we dropped off the CN Tower in Toronto is given by this formula S. And we calculated the average velocity of the ball from the interval from t equals 5 to some other time t equals t, some other time in the future. And we came up with this formula for average velocity. Okay, so this formula represents the slope of the blue line, right? And that blue line is called a secant line. And it appeared that as we let the varying point t, s of t move closer and closer and closer to the fixed point, that blue line was becoming closer and closer and closer to a tangent line. And it appeared that the slope of that tangent line was negative 49 meters per second. So to write that fact using limit notation, we would write the limit as t approaches 5, right? So we're letting that time in the future is varying point t, s of t. So we're letting this t time approach 5. Okay? Letting this point get closer and closer and closer to the fixed point. So the limit as t approaches 5 of the average velocity, which we know is given by that formula up there, negative 4.9 t squared plus 122.5 over t minus 5. The limit of that expression as t gets closer and closer to 5 is negative 49. So that's our limit notation. In class, we discovered this important fact we're going to write as an analogy. So average velocity is to blank line as instantaneous velocity is to blank line. How do I fill in the blanks? secant and tangent. Good. The slope of a secant line tells you the average velocity between 2 points, and the slope of a tangent line gives you the instantaneous velocity at a single point. So the process of finding slopes of tangent lines is critical to success in this class. We could probably rename Calculus 1 Tangent Lines 1. Okay, this is everything we're going to be doing has to do with tangent lines. And finding the slope of a tangent line depends on the idea of a limit. So today we talk more about limits. So here's a true life example that I thought about probably 4 or 5 years ago. I got a little nervous about the amount of caffeine I was drinking. So a cup of coffee contains approximately 100 milligrams of caffeine. The half-life of caffeine in the human body is about 6 hours. And that means that your body metabolizes and eliminates about half the caffeine that you take in every 6 hours. So if you drink 1 cup of coffee on Monday morning, how much caffeine remains in your system 24 hours later? A 16th? How'd you get that? How'd you get that? Yeah. 25 milligrams, yeah. Yeah. But you totally were doing it right. 24 hours. Yeah, so 1 over 32 what? Of 100. Yeah, good. Yeah. So you say, okay, let's see, 24 hours. How many sets of 6 hours are in 24 hours? 4. So I'm going to half it 4 times. I'm going to take my 100 milligrams, and over the course of 24 hours, I'm going to eliminate half of what's in my body 4 times. So over the first 6 hours, I go to 50, right? And then I half it again, I go to 25. And I half it again, I go to 12 and a half. So that's 1, 2, 3 halvings. One more time, 6.25 milligrams remain. So this is 6 hours, 12 hours, 18 hours, and then finally 24 hours. 6.25 milligrams of caffeine. But it's 24 hours later, a full day has passed, and I go buy another cup of coffee, right? So I add another 100 milligrams of caffeine into my body, and I still have 6.25 milligrams coursing through my veins, right? So add that amount to my 100 milligrams from my Tuesday morning cup of joe, right? So I now have 106.25 milligrams. 24 hours later, Wednesday morning, right before I drink my morning coffee, how much caffeine is in my system? .64. How'd you get that? Divided by 16 again, because you're going to half it 4 times. Okay, so we do 106.25. And we're going to divide by 2 to the 4th, because we're halving 4 times. 2 to the 4th is 16. And that comes out to, say it again, 6.64? 6.64 milligrams. So there's a little bit more caffeine in my system Wednesday morning before my cup of coffee than there was Tuesday morning, right? So how much caffeine is in your system on a Friday morning before you drink your daily cup? Assuming you drink Thursday also, yeah. Take a couple minutes, figure it out in your groups. All right, what do people get? 6.67 about. Can you explain how you got that? Mm-hmm. Mm-hmm. Which is what? That's the start of Thursday morning. And then add 100. Okay, so 106.67 divided by 16. Friday morning. And it comes out to 6.67 again. You got 6.67 twice. So this is Thursday, Friday. How other people got this? Yeah. Okay, good. All right. How different? Okay. Okay, so when I started thinking about this question, I was worried that it might be possible to like OD on caffeine just by drinking a cup a day, because your body never finishes eliminating it before you drink another cup. So I was like, does it build up in your system? Do you eventually have like all this caffeine? So what do you guys think? Does it build up? Yeah, there's a limit. And that limit looks like it's about 6.67 because we got 2 days in a row. Yeah, for 100 milligrams. 2 days in a row, that was the amount left over after 24 hours. So if you drink 100 milligrams a day, you really are experiencing about 106.67 milligrams a day as the limit in how much caffeine your body is handling. All right, so given that you never fully eliminate any cup of coffee that you drink, can you overdose on caffeine just by drinking a cup a day? No, there's a limit. So the amount of caffeine in your blood does not increase without bound, even though you're adding to it every day. Okay, it approaches a limit. So we could say the limit, sort of in fuzzy math notation, as t approaches infinity, right? So as time stretches on, the limit of the amount of caffeine in my body, we'll call it C, is what? 6.67 milligrams. All right, so let's look at some more generic mathematical functions. So this was a function of how much caffeine's in your body, right? We're going to look at some more generic ones and try to develop the idea of a limit. Yes, only with a 100. And the limit will change, yes, yep. Okay, so let's look at the function x squared minus x plus 1. Quadratic. What happens to the function value as the x value gets closer to 2? Gets closer to 3. In fact, we know what happens to that function when x equals 2, right? We can get as close as we want. We can get right there, right? So let's take a look on the graphing calculator. So we go to y equals, and I'm going to put in neg x squared minus x plus 1. Just go to y equals, type in the function. I want to look at just a standard window, -10 to 10, -10 to 10. So I press zoom 6. That gets me a standard window. And there's my parabola. All right, so I want to know what happens near 2, near x equals 2. So I'm just going to use the trace button. And that just puts a cursor on the parabola, and you can move it left and right with the arrows. So you see the x and y coordinate of the cursor at the bottom of the screen. So I'm going to cursor right and see what happens as my x value gets closer to 2, what's happening to my y value. So as I approach 2, so now I'm pretty close, 1.7, 1.9, and then I jump over it to 2.12. So it looks like as I approach 2 from either side, my y value is approaching 3. And we can double check with the table. Go to your table. I'm going to clear the things that are in here. I want to know what happens as I get close to 2. So I'm going to get close to 2, like 1.9, 1.99, 1.999. My y values are getting close to what value? 3. And I can approach from the other side too. Like I could do 2.1, get close to 2 from a little bit to the right of 2, 2.01, 2.001. It appears that from that side, my y values are also getting close to 3. And because this is a special kind of function, I could plug 2 right in and see that the y value is 3 right at that point. So this is kind of a straightforward example because you can just plug in to get the limit. So I would say the limit as x approaches 2 of this function x squared minus x plus 1 equals 3. As I get close to 2, as I get close to x equals 2 from the left and the right, my y value gets close to 3. So here's an informal definition of a limit. Okay. We write the limit as x approaches a of f of x equals L. Okay. If the values of f of x can be made as close to L as we want by taking x values sufficiently close to a. So I can get my y value for f of x. I could get my y value as close to 3 as I want. I could say I want my y value to be 2.99999. And I would say, okay, that's easy. Just make sure that x is 1.9999997, right? Whatever I want my y value to be, as close as I want it to be to 3, I can get there by choosing x appropriately. So there's a more formal definition of a limit. It's called the epsilon delta definition. And it's basically just a formal way of writing out this as close as I want definition. We're going to skip it. You can read about it in your book if you're interested. And you can see me outside of class if it intrigues you. All right, so using a graph on your calculator and a table of values, we want to guess the value of this limit. So we go to y equals. We type in x over, and then the square root of x plus 1, close the parentheses, minus 1. And I want to know the limit as x approaches 0. So in the last example, I could just plug in. I just plugged in the 2 to get the limit. Nice, easy example. In this case, if I try to plug in 0, I end up with 0 over 0, which is not defined. So I'm going to have to do a little bit more investigation to figure out what this limit is. So that's why I need the graphing calculator. So I'm going to look at a table of values. Oops. And I'm going to type in values close to 0, from the right of 0 and from the left of 0. So what are some values close to 0, or just any value close to 0 but to the right of 0? So I could do 0.1, 0.01, 0.001. What value does it look like the y values are approaching? 2. Okay, and then let's just double check, make sure we come from the other side, you get the same value. So I'll do negative 0.1, negative 0.01, negative 0.001. Does it look like those y values are also approaching 2? Yes. Okay, so we're going to say that the limit as x approaches 0 of x over square root of x plus 1 minus 1 is 2, even though we can't plug 0 into that function, right? If I try to just type in a 0, I get an error. I can't divide by 0. So this case is a little bit different than the last example because you can't just plug in. We actually have to look at what value the function is approaching. You can't tell what value the function is at 0. Okay, so the most important limits that we're going to see this year are going to be fractions, where you appear to get 0 in both the numerator and the denominator when you plug in, just like this previous example. So here's another one. What happens if I try to plug 3 in? I'm trying to take the limit as x approaches 3 of x squared minus 9 over x minus 3. You get 0 over 0. Okay, so I can't just plug it in. So I could investigate with my calculator, or I could do some algebra and try to make it not 0 over 0. So what do you notice about x squared minus 9? Yeah, x plus 3, x minus 3 over x minus 3. And they cancel, right? I can get rid of my x minus 3's. So then I have the limit as x approaches 3 of x plus 3. And now what happens when you plug in? You get 6. Yeah, you can evaluate it, and you get 6. Let's double check that this works by using our calculator to investigate this limit. So we go to y equals. I'm going to type in my function x squared minus 9 divided by x minus 3. Go to my table, and I'm going to plug in values closer and closer to 3. All right, so values that are close to 3 but a little bit to the right of 3 could be like 3.1, 3.01, 3.001. Definitely looks like the y values are approaching 6. And then I can go from the approach 3 from the other side, 2.9, 2.99, 2.999. Again, looks like the y values are approaching 6. Okay, so this factor and cancel method seems to work. So that example is something that we call an indeterminate form of the type 0 over 0. When you get 0 over 0, it just means there's more work to be done. Work by work, we mean algebra. Try to turn it into something that is not 0 over 0. Okay, so the first thing to try when you see a new limit is to just plug in, right? If you can plug in and you get a value, then you're done. Okay, unless you get an indeterminate form, there's nothing else to do. When you get an indeterminate form, you have to try to do a little finagling to maybe try to get something to cancel. And in the last resort, if you can't get anything to cancel, is to use your calculator to investigate. Okay. All right, so in your groups, I'd like you to work on these 3. See if you can evaluate these 3 limits. So the first thing you should try, remember, is plug in. So what do you get when you plug in x equals 5 into this rational function? 0 over 0. Okay, so more work to do, right? By more work, we mean just algebra. Just try to simplify whatever you can. So these are both quadratics that factor. This factors to x minus 5, x plus 2 over x minus 5, x plus 1. Did I do that right? Okay. So my x minus 5's cancel. And so my limit, now when I plug in 5, I get 7 over 6. 7/6. Okay, so for B was a little bit of a trap, giving you 2 quadratics again and making you think that you should factor and cancel. But when I plug in 1, I get 1 plus 4 is 5 minus 5 is 0 over 6 plus 5 is 11 minus 24 is negative 13. That's not 0 over 0, right? That's not the indeterminate type. What is 0 divided by 13 equal? 0. So I'm taking the limit. So when I plug in 1 here, I get 0. That's my limit. So if you plug in and you get a number, that's your answer. The only time it's not your answer is if you have 0 over 0. So for C, when I plug in 5, what do I get? 5 over 0, right? Which is not the indeterminate form 0 over 0. So we could, but it is undefined, right? So you cannot just plug the 0 in. But we can think about what happens as x gets closer and closer to 5. Okay. So my numerator is going to be approaching 5. So the numerator is approaching 5, and the denominator is approaching 0. So they never actually get to 0. Never actually gets to 0. It just gets tiny, right? So think about a fraction and making the denominator smaller and smaller and smaller and smaller. What happens to the value of the fraction? It gets bigger. Yeah, a fraction with a smaller denominator is a bigger value. Like think of a half compared to a third, right? A half is bigger because its denominator is smaller, right? So when you have denominators that are getting smaller, the value of the fraction is getting bigger and bigger and bigger and bigger. So this is blowing up, right? So my limit is infinity. It's just getting bigger and bigger and bigger. So let's take a little look at the graph just to verify that that's what happens. So x over x minus 5. And I'm going to do a zoom 6 just to get a standard window. And it actually looks like I forgot to consider something. Right? When I approach 5 from the right, the graph of the function graph blows up, right? But when I approach from the left, when I approach x equals 5, the y values of my function go way down, right? So we should say this isn't necessarily infinity. We should say it does not exist. Right. Yeah, one side blows up, the other side goes down. Limits from the two sides are different, right? So you can't say that there is a single limit. Okay, so why does one side get big and the other side gets small? Why does one side go to positive infinity and the other side goes to negative? Algebraically, why is one side positive and one side negative? The denominator would be negative, yeah. So your numerator is always positive no matter which side of 5 you approach from. But your denominator, if you approach from the right, you get a positive value. And when you approach from the left, you get a negative value. So you're still in absolute value, things are getting huge, but you're dividing by either a positive or a negative. So it either grows really big or it grows really small. All right, so we just saw an example where the two limits from different sides were different. So sometimes it's useful to consider limits from each side separately. One-sided limits are denoted with a little plus or a little minus next to the limiting value. We would say the limit as x approaches a, and this little plus means from the right. And this little minus means from the left. So your pictures in your packet are not very good. I apologize. They printed funny. So you can look up here and kind of fix them if you can. So I want to find the one-sided limits using good notation for this picture on the left. So here's my function, and I want to find the one-sided limits as x approaches 2. So I want the limit as x approaches 2 from the right of f of x, and the limit as x approaches 2 from the left. Okay, so looking at this graph, go to the right of 2, and as I approach 2 from the right, what y value is my function approaching? 3. Even though it's not defined at 3, that's what it's getting close to. But if I approach from the left, move to the left of the 2, and follow the graph towards x equals 2, what y value is my function approaching? -1, even though it's not defined there. That's the y value it's getting closer and closer to. So we should see that in that question, the limit as x approaches 2, if I don't define what side I'm coming from, doesn't exist. It approaches 2 different values from the left and the right. So we say that that limit does not exist, which we often abbreviate with DNE. Okay. So it should be clear that a limit will exist if and only if the one-sided limits both exist and are equal. So our only concern when we're finding a limit is analyzing the behavior of the function near the given x value, not at the x value. Okay, so the value of a limit has nothing to do with the value of the function at x. So think about it in terms of this one. What is the value of the function at 2? 1, yeah. Yep. So my two-sided limits, my two one-sided limits are different than the value of the function. Okay, so sometimes they're related, but oftentimes they're not. How did I get f of 2 equals 1? So my function was undefined. These two circles were open, and I have a closed circle here. So this is a piecewise function. And remember that any function can only be defined, you remember the vertical line test? So my function value, my function only touches at this one point here. F of 2 is 1. So it's just not a continuous function. Okay, so let's talk through, but not write down formally, the one-sided and two-sided limits at x equals -3 for these graphs. Again, your pictures aren't very good, so you can look up here. Mine aren't that great either, but they're better. Okay. So for part A, what is my limit as x approaches -3 from the left? 2. And my limit as x approaches -3 from the right? 2. So as I approach from the left and from the right, they're both 2. Now how about B? Slightly different picture. What's my left hand and right hand limit? 2. Right? It doesn't matter that I put this little dot in here to define. So in part A, the function is just not defined at -3. There just is no value for the function at -3. But it still has a limit for x equals -3. For B, the function is defined at -3, but it's different value than the limit. And for C, what's my limit from the left and the right? 2. So my limit is 2 again. And that happens to be my function value. So you can see that the function value really has nothing to do with the limit. The function cannot exist. The function can be defined at a value different than the limiting value, or the function value and the limiting value can be the same. Okay, here's some limits that have to do with end behavior. So instead of approaching a specific value, we're approaching infinity or negative infinity. We're letting the x values get really, really, really big in magnitude. So think about x to the 4th. What happens as you let the x values get huge? What happens to x to the 4th? It gets huge. And what happens to x to the 4th as the x values get really, really, really negative? It still gets big, right? Because when you raise something to the 4th, whether it's positive or negative, it becomes positive, right? So that also goes to infinity. So that's just the notation for end behaviors. And end behavior, I'm sure, is something that you've studied in a college algebra or pre-calc class. class. Okay, so here's a new limit. The limit as x goes to infinity of the cosine of x. Right? So what happens to the value of cosine as you let x get bigger and bigger and bigger? Yeah, it oscillates, right? Cosine x looks like this, etc. Okay. So as my x values get bigger and bigger and bigger and bigger and bigger, my cosine value never settles down anywhere, right? It just keeps oscillating around 0. So we say that this limit doesn't exist. It never settles down at one particular value. Okay, so that brings us to our group activity called Take It to the Limit. I did not give you an answer key for this one, so I want to make sure that you discuss with your classmates the answers that you get. So for each of these limits, I want you to investigate it numerically, which means use a table in your calculator. Be sure to approach your A value from the left and the right. 3, make a guess about the limit based on your table. And then part C, see if you can confirm the limit algebraically by plugging in or by doing some algebra and then plugging in.